talked about projections last week. Just a very, very quick recap. The most naive kind of projection, or the simplest kind of projection, was just where you forgot about the z coordinate. Has been aligned. So the viewpoint is at the origin, and the center of view, or the direction that the camera is looking, is along the positive z-axis, as illustrated in figure 7.1. And so you can quickly get a projected image by just forgetting about the z coordinate. Just plot all points using their x, y coordinates, plot them on the z equals 0 plane, and then everything in the scene will just be rendered on this two-dimensional xy plane. And, you know, there's certain good things about orthogonal projection. Preserves angles, and we discussed lots of this thing. Parallel lines, go to parallel lines, preserves angles, things, you know, objects which are the same size, no matter where they are in the scene, they'll be projected to projected figures with the same size, so it preserves size in a way. But of course, it doesn't really look like how we visually perceive the world. Because when we look at the world and we see parallel lines, if you're standing at the center of a long road, in the distance you see that the lines tend to move together. Because of your 3D vision, you're seeing two slightly different images from your two different eyes. Your mind compares those two different images and produces a view of the scene where you can perceive depth. You can tell whether things are close to you or far away. But none of that kind of information is present in the orthographic projection, because it just flattens everything vertically, perpendicularly onto the xy plane. So it wouldn't be very satisfying to play your 3D computer games with everything just orthographically projected onto the screen, because it just wouldn't look realistic at all, and you wouldn't be able to view depth or anything in the world. Okay. We did oblique projections, which was just like orthographic projection, but just at an angle to the viewing plane, not directly perpendicularly onto the angle to the viewing plane, but projected slantways. But the real proper kind of projection was perspective projection, and this will produce a projected image on a two-dimensional plane, a projection plane, which you think of as being the screen, computer screen, which does carry all the depth information and which produces something approximating what, you know, something approximating the images we actually see in our minds when we look at the three-dimensional world. And so again, the environment is aligned, the viewpoint at the origin, looking along the direction of the positive z-axis. And the way perspective projection works is we join every point, every vertex in the environment gets joined by a straight line to the origin, which is our eye or virtual camera, like a pinpoint eye or a pinpoint virtual camera. And this mimics what goes on in reality, because you can think of these projector lines as being the light rays. So the eye or the camera is only going to perceive those light rays that hit it, yeah, hit the actual point of the camera. And so how it sees each vertex is just by seeing a light ray coming in a straight line from the vertex to the eye of the camera. And so a projected version of the scene is obtained by positioning this projection plane between the camera and the environment. Okay. In reality, of course, the actual projection plane is at the back of our eyeballs. So you have an upside down image and it's on a curved thing, and it's all kind of biological, so it's not really vectors and stuff. It's all done with cells and stuff. So, you know, lots of interesting complications in how we actually perceive things, but you know, we simplify it mathematically and produce something which we can calculate on a computer by, you know, if you like, taking your retina from the back of your eyeball, straightening it into a plane and pushing it in front of the eyeball so that things land on this projection plane, and their projected positions are recorded in the points where they intersect the plane. Okay. And all you need to know about the plane, aside from the usual setup of the aligned environment, camera at the origin, looking along the positive z-axis, the only thing left to specify about the setup then is just where the plane is. Now it's going to be perpendicular to the parallel to the xy axis. So all that we need to define the projection plane is just the distance f. Okay, just it's where the projection plane is on the z-axis. Okay. Then we discussed last time, okay, how we actually implement this, how we actually calculate it. So given the setup, and given the three-dimensional or four-dimensional homogeneous coordinates of all the points in the environment, how ultimately are you going to calculate these points on the projection plane? Let me describe that. We want to use matrices as much as possible to be consistent with our other transformation and calculation methods. So we described last time how we make use of this projection matrix, which it leaves the x, y, z coordinates unchanged, but what it does do is it changes the fourth homogeneous coordinate. Okay. So in the initial setup, each point in the environment has a vector of coordinates like this, an x, y, z coordinate, and a 1 as the fourth homogeneous coordinate. After multiplication by this projection matrix P, it changes the fourth coordinate to z over f. And then after multiplying all the vertices by this matrix, we then use the convention, we then adopt the convention for what actual three-dimensional point is represented by a set of four homogeneous coordinates like that, okay? And the convention is that you always divide everything by the fourth coordinate in order to obtain the actual x, y, and z components. So dividing x, y, and z by this scaling factor z over f produces these coordinates, xf over z, yf over z, and f. So these are now the coordinates of the projected point on the projection plane. Remember, the plane is positioned at the z value, z equals f, and you can see that happening here. All these points now have third coordinate f. No matter what the x, y, and z were, the third coordinate is now always f. So these are indeed all points on the projection plane. And the first component is this xf over z, and the second component is yf over z. Okay. So we looked at that calculation method last time. We drew some diagrams in answer to exercise 7.2 there to confirm that these were indeed the correct values that the projected points ought to have. Then looked at an example of vanishing points. Okay, so there's this idea that parallel lines, when you look at them in the environment, if they were carried on sufficiently long, like a road disappearing into the distance or train tracks disappearing into the distance, they appear as if the parallel lines actually meet somewhere at some distant point in the horizon. This is a property of the perspective projection called vanishing points. See here a cube, and there's two sets of parallel lines on the cube, and they've got two different vanishing points for those lines. And we showed how to calculate the positions of those last time. Okay, there's an application of this. So what we're going to pick it up today with is this application of back projection. Okay, now back projection is the problem of trying to reverse the projection process. Now, first of all, we must remark that, so how do I describe this? Yeah, so the kind of setup to think about this is if someone were playing a computer game like this, so we think of this projection plane as being the screen, and the user is interacting with the computer, and they click somewhere on the screen. In the simulation of the environment, this click on the screen is supposed to represent clicking some point in the three-dimensional environment. So the basic problem is, given a position on the projection plane, can you work out what position in the environment that represents? Now, just stated like that, it's not a valid problem. It can't be solved because it doesn't have a unique answer. Okay. Because when you look at the diagram of perspective projection, you know, it's obvious that every point on the screen, on the projection plane, is coming from an infinite number of points in the three-dimensional environment. Every point on this projector line will get projected to this actual point here. So if the user clicks on that point on the screen, how is the computer meant to know, or how are you meant to infer what actual point in the 3D environment they were trying to indicate? Well, you can't, because there's an infinite number. So you need to present a little bit more information. So one way of doing that is to solve this back projection problem for the case of a line. So in the environment somewhere is a line joining 2 points, P1 and P2, in the three-dimensional environment. Now that line gets projected onto the plane as shown here. So we got points P1 prime and P2 prime. They're the projections of P1 and P2. So P1 prime and P2 prime are 2 points on the projection plane. And this line between P1 and P2 has a projected version as well. So that line gets projected onto the projection plane as a line. And so what we're going to do is solve this problem. If we specify a point on this line in the projection plane, so if we click on the screen, and this is recorded as specifying a point on the screen, but also the extra information that it's a point on this line, this particular line, can we then back project, if you like, and obtain the actual point in the 3D environment, which will be on the line, on the original line, that we indicated here, okay? Now, you can see now how that's becoming, you know, it readily looks like some kind of vector line intersection problem, okay? We've got this line here, which is living in the projection plane. We've got a projector line, which is like the ray of light that comes from the 3D environment into the eye. Follow this out from the eye back into the environment. Okay, it's hitting a point here on the screen, on the projection plane, but continue it on out. And where does it intersect the actual line? Okay, so it's beginning now to look like just some kind of classic kind of vector line intersection problem, which, you know, if we tackle it carefully, we should be able to solve. Okay, so that's what we're going to do now. As an application of this, application of these ideas. So, keep that diagram in your mind, or keep it on view in front of you. So what have I called this? This is exercise 7.4. Okay, I won't bother reproducing that diagram on the notes because everybody has it in front of them. So, so we're given that information, P1, P2, P1 prime, P2 prime. Now we just need to, because we're going to have to get down to the coordinate level, or the component level of these vectors, we'll introduce notation for them. So I'm going to let P1 be x1, y1, z1, and P2 be x2, y2, z2. Well, if we name the components of P1 and P2 like that, then we know what the components of P1 prime and P2 prime are going to be. They're projected versions. Okay, we know that they're going to have coordinates f, z1, x1, f, y1 over z1, and the third coordinate will be f, so it's a point in the projection plane. And P2 will be the same thing, but just f over z2, x2, f over z2, y2, and f is the third component. Okay. Now the line in the world space is given by the usual vector equation of a line. So the usual vector equation of a line between 2 points is going to be P1 plus mu P2 minus P1. Okay, so everybody remember, like, the idea behind this. This is R. This is a general position vector on the line. And it's made up of, say, the vector p1. So you hop from the origin to p1. And then you go some multiple mu along this vector here, p2 minus p1. But p2 minus p1 is just the vector joining the point p1 to p2. So it's the direction vector of that line in the environment. So mu is a parameter here. So mu is just some real number. The projected line, similarly, has vector equation R. Well, it's just the primed version of that for some nu in R. So sorry, that's the Greek letter nu, which kind of looks like a V, lowercase v. You could just write it as a V, I guess. So these are our two lines. So what is the problem? The problem is, see, we're going to click on the screen. So we're going to take as a given the point on the projected version of the line, and then try and work out what the corresponding point is on the real line in the world space. So our problem becomes in the notation that we've introduced here. Given the value of nu, find the value of mu. So the value of nu will define a point on the projection plane, because it will define a point on the projected line, and we want to obtain this parameter here. And if we have the parameter mu, that will specify the point on the line in the actual world space. So if you look to the diagram associated to this problem, what we have to now do is we want to consider this line, this projector line, which is intersecting the line in the projection plane at a given point. We want to continue that out and work out where it intersects the actual line in the world space. Okay. So we let some value of this parameter nu be given. The equation of the projector line, i.e. the light ray emerging from the camera, from the virtual camera, well, this is another vector form of a line, and it's just going to be any multiple of this vector here. Okay. So when lambda equals 0, you're at the 0 vector, you're at the origin. And as lambda increases, you're at various positions on the line coming out from the camera there in the diagram, which is going to go through the projection plane and carry on and intersect the original line in the world space somewhere. This light ray, if you like, this intersects the original line. Just you see, when lambda equals 1, you're at the point p1 prime plus nu p2 prime minus p1 prime. You're at the point on the projected line on the projection plane. So between 0 and 1, you're between the camera and the projection plane. When lambda equals 1, you're actually on the projected line on the projection plane. Then when lambda goes beyond 1, then you're going out beyond the projection plane, and at some value of lambda, you're going to intersect with the actual original line in the environment. So this light ray intersects the original line when r, this position vector, which in one sense is given by this equation, okay, that's what r looks like as a point on the light ray, but we want to also see it as a point on the original line in the environment. So it has to also be equal to P1 plus mu P2 minus P1. Okay, because this is a point on the light ray, if you like. And this is the point on the original line in the world space. Okay, so what we've done there is kind of encoded the problem or set up the problem purely in terms of all the vector information in the setup. Okay. Now there's so many variables in this thing. It's easy to get lost and kind of not know how to proceed or how to solve it. So you need to not get swamped by all the different parameters, but just remember what's going on. We stated the original problem that we were given a value of nu, and we had to find the resulting value of mu. So mu is the goal that we're looking for. And then you look at this problem. Okay, so in a sense, mu is in this equation, so maybe we can solve for mu. But just also look at, what values here do we know? What's part of the setup and what maybe isn't? Well, all the p's are part of the setup. Okay, the original positions of these points 1 and point 2, their projected versions, P1 and P2, that's all part of the original setup. Nu, we're thinking as a given quantity into this problem. So we're looking to find the value of mu, but we've also got this other parameter lambda hanging around, and we don't quite know that either. Lambda, in a sense, is like an equivalent thing to mu. Lambda is the parameter that gives you the point we want on the light ray, whereas mu is the parameter that gives us that same point on the original line in the world space between P1 and P2. So lambda and mu are kind of playing equivalent roles, but they're parameters for the same point, but describing that point as lying on different lines. Okay, so you certainly don't want to try and work towards some final solution which has a lambda in it, because lambda is in some sense the goal as well. So, so what we're looking to find here is to solve this equation. We'll call this equation 1. To solve equation 1 for mu. And obtain some value for mu, but which only involves things which are parts of the setup. Okay? So we only want to have setup variables in here. So the setup are any of the p's, P1, P2, the projected versions, or any of the components, and we can allow the parameter nu to be in here, because that's part of the given. Nu describes the point on the screen we're clicking on, and also maybe f. F is part of the original setup as well, the actual position of the position of the projection screen. But we don't want to see lambda in here. You don't want to see lambda in there. Lambda is, you could phrase the thing as solve it for lambda either. Lambda is a parameter on the light ray, which is going to give us our solution point that we want. Now, but we're phrasing it in terms of solving for mu. So we want to eliminate lambda from the thing. Now this, in some ways, this looks like maybe an unachievable problem because this is only one equation, but it's got these two unknowns in it, lambda and mu. Now lambda and mu are real numbers, but of course this isn't really just one equation. It's a vector equation. It's an equation which says this vector on this side is equal to that vector on this side. And we're in a three-dimensional environment. So actually, every vector here has three components. So really, this is three equations. It's three equations. When if you get rid of the vectors and replace them, you know, if you look down on the component level, this is really three equations. So now a set of three equations with just two unknowns in it, well, now that does look achievable. Three equations, if there's only two unknowns, you should be able to, you know, if there is a solution to the problem, and the way we've set the problem up, there will be, okay, because we're talking about a line, original line, and its projected version, and taking a point in the projected line back to the original line. So there will be a problem. So we should have enough information here to solve it, because really we've got three equations here, and there's just the two unknown quantities. Okay, so we proceed by looking at the components, looking at the components of equation 1. So now the simplest one to look at first will be the z component. And that's simple to look at because remember the projected variables, the projected points, they all have the same z coordinate because they're all living on the projection plane. So they all have third coordinate f. So if we look at the z components of this vector equation, that'll be quite simple because on the left-hand side, see, what's the third component of this vector? It's just so this RZ, it'll be lambda. The third component of P1 prime is F. P2 prime is F minus F. So that's just equal to F lambda. Okay, that's from the left-hand side. From the left-hand side of equation 1. From the right-hand side, we want to look at the third component of this right-hand side. Now, the third component of P1 is Z1. Mu is the unknown parameter we're trying to solve for, and then Z2 minus Z1. So that gives us one equation, that F lambda is equal to Z1 plus mu. So we want to bank this. What do I call it? A. So that's one equation. We'll get another equation if we look at one of the other components of equation 1. Z1 was particularly nice, so we could look at either the x or y. It doesn't really make a difference. But let's look at the x component. So Rx, if you just look at the left-hand side of equation 1, you've still got it up there. The left-hand side will be lambda. Now, at the start of the problem, we wrote down the first coordinates of the projected points P1 prime and P2 prime. So P1 prime has coordinate f x1 over z1. And this is plus mu into fx2 over z2 minus fx1 over z1. Yeah, okay, so that's from the left-hand side. That's from the right-hand side. So I'm referring here to the left-hand side and right-hand sides of equation 1. The right-hand side of equation 1, looking at its x component, we see just x1 plus mu x2 minus x1. So we've got this left-hand side equal to this right-hand side, so we'll kind of bank that. Now, see, on the left-hand side, there's a common factor of f in everything. So I can bring that out to the front. So it's saying f lambda into x1 over z1 plus nu x2 over z2 minus x1 over z1. This equals x1 plus mu to x2 minus x1. Call that equation B. Now, always there's the danger of getting lost in the algebra, getting swamped by all the stuff, forgetting what's going on. Remember, we articulated the problem above. We said, given the value of nu, value of mu. And then up here, didn't I say, we kind of pause for a minute to gather breath. What we're looking for here is some solution that says mu is equal to some kind of thing, some kind of expression. And the things we're going to allow in there, or we're going to expect to see in here, are any parts of the setup. The vectors p1, p2, or their components, because they're specified in terms of their components. The given input, the click on the screen, if you like. The distance f of the projection plane from the camera, that's part of the original setup. But we don't want to allow in is lambda. Lambda is kind of this equivalent parameter to mu. So have we done enough so far? We've got two equations now. They both feature the two unknowns, lambda and mu. Lambda and mu. And everything else in the equations, the f, z1, z2, z1, f, x1, z1, that's all part of the setup. So those are all known values. Black pen gone. There it is. So this looks OK. You see, in fact, A is giving you a value for f lambda. A gives you a value for f lambda in terms of known stuff, z1, z2, and mu. So if you imagine this right-hand side stuck down here, you'd have f lambda. Instead of f lambda here, you'd have this quantity, z1 plus mu, z2 minus z1. Multiplying this, but everything is known here, and everything is known here apart from this mu again. So if we substitute A into B, replacing f lambda, we should just have one equation and one unknown, which should be solvable. So we're replacing f lambda. We get the solution mu equals, well, what kind of solution do we get? Now, I've just about run out of patience with that, all that messing around with algebra. Any reasonable person would just kind of say there must be an easier way. So there's a bit of algebraic manipulation to do there, but we can get the computer to do it quite easily. Now, this isn't using MATLAB. This is done using Sage. Has everybody got the notes there? Yeah. OK, so MATLAB, you can do similar symbolic or solving of symbolic equations using the sims command. So you can look up help for that. But here's how you could do a similar thing with Sage. So we're looking at our equation that we've got. So we just want to name all the parameters. Well, there's a mu in there. There's an x1, an x2, a z1, a z2. What else is in there? The f and lambda have gone because we're substituting them out. Is that everything? U, x1, x2, and the nu is in there as well. Okay, so we need to set up all those variables. And then we'll define the equation. So what's the left-hand side of the equation? The left-hand side, well, you're replacing, so we're looking at equation B, and you're replacing the f lambda. So you're replacing f lambda with z1 minus u, z2 minus z1. It's z1 plus, sorry, plus. Okay, so that's multiplying the left-hand side, the other factor in the left-hand side of B, which is x1 over z1 plus mu into x2 over z2 minus x1 over z1. So that's what we want to solve. Remember, when you're representing an equation symbolically in MATLAB or in computer systems in general, the convention is to use a double equal sign. So double equal signs the right-hand side. The right-hand side is slightly easier. X. Look at it. So you can still can't see it. The monitor switched off. Okay, here we are. x1 plus, this is mu into x2 minus x1. That's the right-hand side. I'll get it to show me the equation. It should show me a nice typeset version of the equation. Substitution using, I've done something, well, I've missed out a multiplication sign there. Okay. Does that look right? Everyone agree that that's the equation we want to solve after we substitute A into B? So we just want to solve equation. Now we have to tell it which variable to solve for. We're solving here for mu. We want to work out what mu is in terms of everything else. Seems to have solved it without any complaint. Get it to show us the solution. Ooh, nice. Get this nice solution for mu. Just checking it looks kind of reasonable, yeah? All the ingredients on the right-hand side, the parameter nu, z1, z2, that's all part of the original setup. And also notice that any dependence on the x has gone. Any dependence on the f has also gone. That's interesting. So we're just seeing dependence on the input parameter nu, which is the parameter for when you clicked on the point on that line on the screen. It's the parameter that describes where along that line you are, and the z coordinates of the original point. Okay. I'm just going to copy that down. So this gives us the solution mu as nu z1 over nu z1 minus nu minus 1 into z2. Okay, and so that solves this back projection problem that we set up. Okay, with this value of mu, what role did the parameter mu play? Remember, mu was the parameter which tells you where along the original line in the world space you are. So we have a value for mu now in terms of the setup of the problem and in terms of the input parameter nu. So that could be put back in here, and we recovered this point r, which is the point in the line in the world space. So it's the original point in the three-dimensional environment that got projected to that. Okay. So that's a good example there that shows you the application of the perspective projection to solving this related problem. Of course, the perspective projection, where did that come in? That came in forming these components for the projected points P1 and P2 prime. These forms of the components for P1 prime and P2 prime, in terms of the components of 1 and P2, these were given by that's the perspective projection happening there. And it's a good kind of non-trivial, or, it's not immediately straightforward or quick through the algebra. You get a whole forest of parameters coming in, which you have to kind of navigate your way through carefully and keep a clear eye on what kind of solution you're trying to get out of it. Okay, better finish there. So on Thursday, sorry, on Friday in the session when I see you, we'll do a lot of preparation work for your next assignment, for the assignment about building your virtual environment, okay? So we'll do some work with MATLAB and programming stuff then.